Hello there, and welcome to Edge of Mind. Tonight, we'll take our time with an idea that feels vast but strangely gentle, a quiet kind of wonder. When you look up at the night sky, you're seeing light that traveled for years to reach your eyes. The darkness between stars holds more distance than you might imagine. Some of that light began its journey when dinosaurs walked the Earth. Other photons started traveling before our sun even existed. Each point of light carries time within it, stretched across the vast emptiness between here and there. But there's a limit to how far you can see. Not because space ends somewhere, like hitting a wall. The limit comes from time itself. Light moves fast, but it still takes time to cross the universe. Since the universe has been around for about 14 billion years, light has only had that long to travel toward us. This creates something like a horizon around us. You can think of it the way you'd think about standing on a hill and looking toward the curved edge of the Earth. If you enjoy these gentle journeys, you are welcome to subscribe for more videos like this. For a moment, you can't see beyond that line, not because there's nothing there, but because the curve blocks your view. In space, time creates the curve. The air in your room stays still while you consider this. Beyond that cosmic horizon, space continues. Galaxies spin in the darkness. Stars are born and die. Planets form and drift through their orbits. All of it happening in a universe much like ours, following the same rules, made of the same materials, but we can't see any of it. The light from those distant regions simply hasn't had enough time to reach us yet. It's still traveling through the emptiness, carrying images of worlds we'll never know. And by the way, where are you watching from tonight? I'd love to see where in the world you're listening from in the comments. Your breath moves slowly as you picture this. Some scientists think our universe might be just one bubble in a much larger space. Like soap bubbles floating in air, each universe would be a separate pocket with its own stars, its own galaxies, its own story, slowly. This idea comes from thinking about how our universe began. In the first tiny fraction of a second after the Big Bang, space itself expanded faster than anything we can imagine. It stretched and grew, carrying matter and energy along with it. But this expansion might not have happened everywhere at once. Picture a pot of boiling water. Bubbles form at different times and places. Each one starts small and grows. Some bubbles rise to the surface, while others form deeper in the water. Each bubble has its own beginning, its own journey upward. The universe might work something like this. Different regions of space could have started expanding at different moments. Each region would become its own universe, its own bubble, complete with stars and planets, and the possibility of life. The quiet surrounds these words as they settle. Our bubble would be just one among countless others. Some might be larger than ours, some smaller. Just for a moment. Some might have different rules for how matter behaves, different constants that govern the strength of gravity or the way atoms hold together. In some bubbles, stars might never form at all. In others, galaxies might be so tightly packed that the night sky blazes with light. Each universe would be a unique experiment in how space and time and matter can arrange themselves. But we'd never be able to visit these other bubbles or send signals to them. The space between universes doesn't work the way the space inside a universe works. There's no path you could follow, no rocket you could build that would carry you from one bubble to another. You can let that thought rest for a moment. Every moment, countless tiny events happen around you. An electron in the wall might move one way or another. A photon of light might pass through a piece of glass or bounce off it. Each of these events seems random when you look at it closely enough. But what if they're not random at all? In the quiet, what if instead of one outcome happening while the others disappear, every possibility actually occurs? Each potential future would branch off like a path in a forest, creating its own version of reality. The room stays calm around this idea. In one branch, you might have chosen to read a different book tonight. In another, a raindrop that's currently forming in a cloud overhead might fall on your window instead of on the grass outside. Most of these branches would be nearly identical to each other. The differences would be so small you'd never notice them. A few atoms arranged differently. A single particle of light taking a slightly different path through space. But over time, small differences can grow into larger ones. In some branches, different people might have been born, Different discoveries might have been made. The history of the world might have unfolded in ways you can't imagine. And gently, all of these realities would exist at the same time, like pages in an infinite book. You'd never be aware of the other pages. Your consciousness would follow just one path, through the branching possibilities. But somewhere else in the vast space of potential realities, other versions of you would be living other lives. The darkness outside holds space for all of this. These ideas about multiple universes sound like science fiction, but they come from taking our best theories about space and time and following them to their logical conclusions. But proving these ideas is incredibly difficult. By definition, we can't directly observe other universes. We can't send a probe beyond our cosmic horizon or into a parallel branch of reality. The evidence has to be more subtle than that. Scientists look for patterns in the light that reaches us from the most distant galaxies. They study the faint radiation that fills all of space, leftover heat from when the universe was young and hot. Very softly, they search for tiny variations in temperature and brightness that might tell us something about what happened in those first moments after the Big Bang. Sometimes they find hints, small irregularities in the cosmic background radiation that might suggest our bubble universe bumped into another one long ago. Patterns in how galaxies are distributed that might reveal something about the larger structure we're embedded in. But these hints are whispers, not shouts. The night air moves gently past your window. The idea of multiple universes changes how you might think about your place in the cosmos. If there are countless bubbles of space and time, each with its own collection of stars and worlds, then our universe becomes just one note in an infinite symphony. But it doesn't make our universe less special, even if there are other bubbles where different versions of Earth orbit different versions of our Sun. This Earth is still the only one you'll ever know. Take your time. This sky is still your sky. These stars are still the ones that light your nights. The multiverse doesn't diminish the wonder of existence. If anything, it multiplies it. Every sunset becomes not just one beautiful moment, but one beautiful moment among infinite variations. Every act of kindness, every discovery, every quiet evening spent looking up at the stars becomes part of a vast tapestry of possibilities. You can rest in that thought. The cosmic horizon that limits what we can see also protects us in a way. It creates a boundary around our observable universe, a space that's large enough to contain billions of galaxies, but small enough that we can begin to understand it. Within that boundary, we can map the positions of stars and trace the paths of planets. We can measure the age of distant galaxies and calculate how fast they're moving away from us. We can study the elements that make up nebulae and discover planets orbiting other suns. All of this knowledge comes from light that has traveled across space to reach us. For a moment, photons that began their journey in the heart of a star millions of years ago carry information about the temperature and composition of that star. Light that has been traveling since shortly after the Big Bang tells us about the conditions in the early universe. Each point of light in the night sky is a messenger from somewhere else and someone else. The messages arrive constantly, a steady stream of information about the cosmos beyond our world. Radio waves from spinning neutron stars, X-rays from matter falling into black holes, visible light from galaxies so distant that we see them as they were when the universe was young. Your breathing slows as you consider this flow of information. Even if we live in just one bubble among many, even if countless other realities branch off from every moment, we're still connected to the larger cosmos through these streams of light and energy. Slowly, the atoms in your body were forged in the cores of ancient stars. The calcium in your bones, the iron in your blood, the oxygen you breathe. All of it was created in stellar furnaces and scattered into space when those stars died. You are made of materials that have traveled across the galaxy, materials that might have been part of other worlds before they became part of you. This connection runs deeper than just the physical elements. The same forces that govern the motion of planets also govern the beating of your heart. The same quantum processes that create light in distant stars also power the chemical reactions in your cells. You're not separate from the universe looking in from the outside. You're part of it, woven into the same fabric of space and time that contains galaxies and nebulae, and all the other wonders that fill the cosmic dark. The stillness in your room reflects the stillness between the stars. Just for a moment, If there are other universes beyond our cosmic horizon, they might contain their own versions of this moment. Other conscious beings looking up at their own night skies, wondering about the nature of existence, feeling the same sense of connection to something larger than themselves. But those other moments, if they exist, are as unreachable as yesterday's sunset. What matters is this moment, this sky, this quiet sense of wonder that connects you to the cosmos you can actually observe and experience. The multiverse remains a beautiful possibility, a reminder that reality might be far stranger and more wonderful than we can currently imagine. But even in a single universe, even within the boundaries of our cosmic horizon, there's enough mystery and beauty to fill countless lifetimes of exploration and wonder. The questions that arise from thinking about multiple universes have been puzzling minds for decades now. The air grows cooler as night deepens. In the quiet, when you try to imagine what lies beyond the edge of what we can see, you're doing the same thing that researchers do when they build their largest telescopes and point them toward the most distant regions of space. They're looking for clues about the bigger picture, traces of whatever might exist beyond our ability to directly observe. One of the most intriguing hints comes from studying how evenly spread out the universe appears to be. When you look in any direction, the temperature of space itself is almost exactly the same. This seems strange at first, because regions of space that are separated by vast distances shouldn't have had enough time to exchange energy and reach the same temperature. It's like finding that two rooms in opposite wings of an enormous building are exactly the same temperature, even though there's no hallway connecting them. Your eyes adjust to the darkness outside your window. The solution might be that these distant regions were once much closer together, back when the universe was unimaginably small. And gently, during those first tiny fractions of a second after everything began, space itself expanded so rapidly that regions that started out in contact were stretched far apart. This period of rapid expansion could explain why the universe looks so uniform when we observe it today. But it also suggests something remarkable about the nature of space and time themselves. If space can expand that quickly, stretching and growing at rates that dwarf the speed of light, then the universe might be far larger than the part we can observe. The cosmic horizon that marks the boundary of our visible universe might be just a small window into something much vaster. The silence around you feels deeper now. Beyond that window, space might continue expanding, carrying with it regions that formed under slightly different conditions. Some might have cooled at different rates. Others might have different amounts of matter and energy. Very softly, each region would develop its own collection of stars and galaxies, its own unique history. These distant regions wouldn't be separate universes in the sense of being made of different stuff or following different rules. They would be made of the same space and time as our observable universe, just stretched so far away that their light hasn't had time to reach us yet. But there's another possibility that emerges from the same rapid expansion. The night holds space for bigger ideas. If the expansion happened once, it might still be happening in some regions, creating new pockets of space even now. Each pocket would begin its own slower expansion, cooling and forming its own stars and worlds. From the inside, each pocket would look like a complete universe, with its own cosmic horizon and its own collection of galaxies. This is where the idea of bubble universes comes from. Not soap bubbles floating in empty space, but regions of space-time that have their own internal expansion, their own physics, their own story of how matter and energy evolved over billions of years. Take your time. The bubbles wouldn't be floating in anything we could point to or travel through. Space itself would be what's expanding and creating new regions. Each bubble would be as real and complete as our own observable universe. You can let that image settle without trying to visualize it too precisely. The forces that hold atoms together might be a little stronger or weaker. The particles that make up matter might have different masses. The rate at which space expands might vary from one region to another. Most of these variations would create regions where stars couldn't form or where atoms couldn't hold together. But some variations might create regions where complexity could develop in ways we've never imagined. The darkness outside your window seems to expand with these thoughts. What makes this idea more than just speculation is that it emerges naturally from our best understanding of how space and time behave under extreme conditions. For a moment, the same principles that explain how galaxies move away from each other, also predict that this process of creating new regions might be ongoing. But testing these ideas requires looking for evidence in the most subtle places. Scientists search for patterns in the faint radiation that fills all of space, looking for signs that our region might have bumped into another one long ago. They study how galaxies are distributed across the sky, searching for irregularities that might reveal something about the larger structure we're part of. The evidence remains indirect, like trying to understand the shape of a vast landscape by examining the shadows it casts. Your breathing finds its own quiet rhythm. Even more speculative is the idea that reality might branch in ways that create parallel versions of familiar situations. This comes from thinking carefully about what happens during the smallest scale events in nature, moments when particles interact and outcomes get determined. At these tiny scales, the rules seem to allow for multiple possibilities to exist simultaneously until something forces a single outcome to become real, slowly. But what if nothing actually forces that choice? What if all the possibilities remain real, each playing out in its own branch of reality? This would mean that every moment when chance plays a role creates a branching point. Every quantum interaction, every random decay of a particle, every coin flip would split reality into multiple versions. The room around you holds steady while these ideas unfold. In one branch, the coin lands heads. In another, it lands tails. Both outcomes are equally real, but they exist in separate branches that can't directly interact with each other. From inside any single branch, you would only experience one outcome, but the other possibilities would continue to exist in their own versions of reality. This branching would happen constantly, at every scale, creating an ever-expanding tree of parallel realities. Just for a moment, most of the branches would be nearly identical to each other, differing only in tiny quantum events that have no noticeable effect on everyday life. But over time, these small differences could accumulate into larger variations. In some branches, historical events might unfold differently. In others, different evolutionary paths might lead to different forms of life. The stillness between your thoughts mirrors the stillness between the stars. What makes this idea scientifically interesting is that it emerges from taking quantum mechanics seriously, following its implications to their logical conclusion. The same principles that allow particles to exist in multiple states simultaneously suggest that reality itself might exist in multiple states. But like the bubble universe idea, this remains extremely difficult to test directly. By definition, we can only observe the branch of reality we happen to be in. The other branches, if they exist, would be as unreachable as the regions beyond our cosmic horizon. The search for evidence becomes a search for subtle signatures, patterns that might reveal the branching structure underlying reality. In the quiet, some researchers look for tiny correlations in quantum experiments that might hint at the existence of parallel branches. Others search for ways that information might leak between branches under very special conditions. Your eyes rest on the darkness beyond your window. These ideas about multiple realities change how you might think about the nature of existence itself. If every possible outcome of every quantum event creates its own branch of reality, then somewhere in the vast tree of possibilities, every story that could be told is being lived out. But this doesn't make any single story less meaningful. The branch of reality you experience is still the only one you'll ever know directly. Your choices still matter within that branch. The relationships you form, the kindness you show, the wonder you feel when looking up at the night sky. All of this remains as real and important as it ever was. And gently, the multiverse, whether it consists of distant bubbles or branching quantum realities, doesn't diminish the significance of individual moments. If anything, it suggests that existence is far richer and more creative than we might have imagined. The cool air moves gently through the space around you. What's remarkable is how these ideas emerge from our attempts to understand the universe we can actually observe. The same telescopes that reveal distant galaxies also provide clues about the early universe. The same experiments that probe the behavior of individual particles also test our understanding of space and time. Each observation adds another piece to a puzzle that might be far larger than we initially realized. The light from distant stars tells us about the composition of those stars, but it also tells us about the history of the universe itself. The behavior of particles in laboratory experiments reveals the fundamental rules that govern all matter and energy. This process of discovery continues every night, as new observations are made and new patterns are recognized, very softly. Radio telescopes listen for signals from the most distant galaxies. Particle accelerators recreate conditions that existed in the first moments after the Big Bang. Space-based observatories measure the faint radiation that carries information about the early universe. The darkness holds space for all of this ongoing exploration. Each new piece of information either supports or challenges our current understanding. Sometimes the new data fits perfectly with existing theories. Sometimes it reveals something unexpected that requires new ways of thinking about familiar concepts. This is how science advances, through a careful accumulation of evidence and a willingness to revise ideas when new information becomes available. The multiverse remains a possibility rather than a certainty, because the evidence, while suggestive, isn't yet conclusive. But the search continues, driven by the same curiosity that makes you wonder about the nature of existence when you look up at the night sky. Take your time. The questions that arise naturally from observing the cosmos lead to ideas that stretch the imagination, even when those ideas remain difficult to test directly. Your thoughts drift with the gentle rhythm of your breathing. What's certain is that the universe we can observe is already far stranger and more wonderful than previous generations could have imagined. The discovery that space itself is expanding, that time can slow down under the influence of gravity, that particles can exist in multiple states simultaneously. All of these ideas once seemed impossible, but are now supported by overwhelming evidence. The multiverse might represent the next step in this ongoing expansion of our understanding, or it might remain forever beyond our ability to confirm directly. Either way, the questions it raises about the nature of reality continue to inspire new ways of thinking about existence itself. The night sky above you contains billions of galaxies, each with its own collection of stars and worlds. Even if this represents only a tiny fraction of what exists beyond our cosmic horizon, it's still more than enough to fill a lifetime with wonder and discovery. For a moment, the patterns we see in that observable universe might hold clues about what lies beyond it. The quiet settles around these possibilities, like snow. When astronomers point their telescopes at the most distant galaxies, they're looking back in time. The light from those galaxies has traveled for billions of years to reach us. What they see isn't those galaxies as they are now, but as they were when the universe was much younger. This creates a kind of archaeological record written in starlight. The most distant objects we can detect are so far away that their light began its journey when the universe was less than 1 billion years old. Back then, the first stars were just beginning to form. Galaxies were smaller and more chaotic than they are today. Your breath moves slowly in the stillness around you. Slowly. But there's something even more distant than the furthest galaxies. If you could look far enough back in time, you would eventually reach a moment when the universe was so hot and dense that atoms couldn't form. Before that point, space was filled with a glowing plasma that light couldn't travel through. When the universe finally cooled enough for atoms to form, that plasma cleared. The light that had been trapped was suddenly free to travel through space. That ancient light is still out there, stretched and cooled by billions of years of cosmic expansion. It reaches us now as a faint radio signal that fills the entire sky. The darkness beyond your window holds echoes of that ancient glow. This background radiation carries information about the early universe, encoded in tiny temperature variations. Some regions were slightly warmer, others slightly cooler. These small differences eventually grew into the large-scale structure we see today. The warmer spots became the seeds of galaxy clusters. The cooler spots became the vast empty spaces between them. But the pattern of these temperature variations might tell us something more. Just for a moment, if our observable universe is just one bubble among many, the way those bubbles formed and separated might have left subtle imprints in this ancient light. The air moves gently through the space around you. Some researchers look for circular patterns that might indicate where our bubble universe collided with another during the early moments of cosmic inflation. Others search for unexpected correlations that might reveal the larger structure we're embedded in. These signatures would be incredibly faint, buried in the noise of other cosmic processes. Finding them requires comparing detailed maps of the background radiation with computer simulations of how different types of multiverse might behave. It's like trying to reconstruct the shape of a vast landscape by examining the patterns in a single drop of morning dew. The search continues with each new generation of more sensitive instruments. In the quiet, your thoughts rest in the quiet between heartbeats. Even if such evidence is found, interpreting it would be challenging. The same patterns might be explained by other processes that have nothing to do with multiple universes. This is why the question of testability remains so important in these discussions. Science works by making predictions that can be checked against observations. When a theory suggests something that can't be observed even in principle, it moves into a different category. It might still be mathematically elegant or philosophically interesting, but it becomes harder to evaluate using the usual methods of scientific inquiry. The multiverse sits somewhere in this uncertain territory. The cool air carries the scent of night. Some aspects of multiverse theories do make testable predictions. If cosmic inflation happened the way some models suggest, it should have left specific patterns in the cosmic background radiation. If quantum mechanics works the way many worlds' interpretation claims, it might affect the outcomes of certain carefully designed experiments. But the multiverse itself, the vast collection of other realities beyond our reach, remains indirect. And gently, the evidence comes in the form of consistency checks and theoretical elegance, rather than direct observation. Does the idea fit with what we know about physics? Does it solve problems that other approaches can't handle? Does it make predictions about things we can actually measure? These questions don't have simple answers. The stillness around you mirrors the stillness between distant stars. What keeps researchers interested is that these ideas emerge naturally from well-established physics. Cosmic inflation wasn't invented to create multiple universes. It was developed to explain specific features of our observable universe. The fact that it might also produce other universes is an unexpected consequence. Similarly, the many worlds interpretation wasn't designed to multiply realities. It arose from trying to understand what quantum mechanics actually means. When fundamental theories point toward possibilities that stretch far beyond what we can directly observe, it raises deep questions about the nature of scientific knowledge itself. Very softly, your eyes rest on the darkness beyond the glass. Perhaps the most honest approach is to remain open to these possibilities while continuing to search for ways to test them. The history of science is full of ideas that once seemed impossible to verify, but eventually became accessible to observation. The expansion of the universe was once purely theoretical. Black holes were mathematical curiosities. Quantum effects were too small to measure directly. Each of these concepts eventually moved from speculation to established fact as new tools and techniques became available. The multiverse might follow a similar path, or it might remain forever beyond our reach. The night air holds space for both possibilities. What's certain is that the search itself leads to new insights about the universe we can observe. Attempts to detect signatures of other universes have resulted in more precise maps of the cosmic background radiation. Efforts to understand quantum measurement have led to new technologies and deeper insights into the nature of reality. Even if the multiverse remains unconfirmed, the journey toward understanding it continues to expand our knowledge. Take your time. The gentle rhythm of your breathing matches the gentle rhythm of cosmic time. In the end, the multiverse represents something larger than any specific scientific theory. It embodies our ongoing attempt to understand our place in existence. Whether reality consists of a single universe or countless others, whether quantum mechanics creates parallel worlds or simply describes probabilities, the questions themselves reflect something fundamental about human curiosity. We look up at the night sky and wonder what lies beyond the horizon of our vision. We peer into the quantum world and wonder what happens to all the possibilities that don't manifest in our experience. We build theories and conduct experiments and create instruments that extend our senses far beyond their natural limits. The darkness above you contains multitudes, whether or not those multitudes extend into other realities. For a moment, each star represents a sun that might warm other worlds. Each galaxy contains billions of such stars. The observable universe contains billions of such galaxies. Even if this represents the entirety of existence, it's already far more vast and rich than any single mind can fully comprehend. But the possibility that it might be just one small part of something even larger adds another layer of wonder to an already wondrous cosmos. your thoughts drift like clouds across an infinite sky. The questions that arise from contemplating the multiverse don't have final answers, at least not yet, but they do something equally valuable. They remind us that reality might be far stranger and more beautiful than we currently imagine. They encourage us to remain humble about what we know and curious about what we don't. They suggest that existence itself might be the most creative force in the cosmos, constantly generating new possibilities and new ways of being. The cool air moves through the space around you, like time moves through space, slowly. Whether you're lying in bed looking up at the ceiling, or standing outside looking up at the stars, you're participating in this vast ongoing story. Your thoughts and dreams and moments of wonder are part of the same reality that includes distant galaxies and quantum particles and the mysterious processes that might create other universes. The boundary between inner and outer space becomes less clear when you consider that both emerge from the same underlying fabric of existence. Your consciousness, whatever it is and however it works, is made of the same fundamental ingredients as the most distant stars. The atoms in your body were forged in the hearts of dying suns. The elements that make up your thoughts were scattered across space by ancient supernovas and gradually assembled into planets, and eventually into living beings capable of contemplating their own origins. The night holds all of this history in its darkness, just for a moment. If the multiverse exists, then this remarkable process of cosmic evolution and the emergence of consciousness might be happening in countless variations across countless realities. Each universe might find its own way of organizing matter and energy into patterns complex enough to wonder about their own existence. But even if our universe is unique, the fact that it has produced beings capable of asking these questions is extraordinary. The silence between your thoughts mirrors the silence between galaxies. In some sense, the multiverse is already here in the form of all the different ways reality could be experienced and understood. Every person who looks up at the night sky sees it through their own unique perspective. Every culture that has contemplated the cosmos has developed its own ways of making sense of the patterns they observe. Science represents one approach to understanding, but it's not the only one. The same stars that inspire cosmological theories also inspire poetry and music and art. The same quantum mysteries that lead to many worlds' interpretations also lead to philosophical discussions about the nature of consciousness and free will. In the quiet, the universe reveals different aspects of itself to different kinds of inquiry. Your breathing slows as the night deepens around you. What remains constant across all these different approaches is the sense of wonder that drives them. Whether you're a researcher studying cosmic inflation or someone simply lying in bed thinking about the nature of existence, you're responding to the same fundamental mystery. Why is there something rather than nothing? How did the universe become organized enough to produce complexity and consciousness? What is our place in the larger scheme of things? These questions don't have simple answers, but they connect us to something larger than our individual lives. The darkness beyond your window extends in all directions, carrying starlight from distances so vast they challenge the imagination. If other universes exist beyond that darkness, they remain invisible to us, separated by barriers of space and time and physical law that we may never be able to cross. And gently, but the possibility of their existence changes how we think about our own reality. It suggests that the cosmos might be even more creative and abundant than we already know it to be. It reminds us that the boundaries of our knowledge are not necessarily the boundaries of what exists. The questions we ask about reality shape the reality we discover. The cool air settles around your shoulders, like time settling around space. When researchers first began mapping the cosmic microwave background radiation, they found something unexpected. The ancient light that fills all of space carries tiny variations in temperature, patterns so subtle they require the most sensitive instruments to detect. These variations tell a story about the very early universe, when it was much smaller and hotter than it is today. The patterns look almost random at first glance, like static on an old television screen. But hidden within that apparent randomness are the seeds of everything that would later become galaxies and stars and planets. Very softly, your thoughts drift through the quiet room, like light drifts through space. The cosmic microwave background represents the oldest light we can observe, released when the universe first became transparent. Before that moment, Space was filled with a hot, dense plasma that scattered light in all directions. When the universe cooled enough for atoms to form, light could finally travel freely across vast distances. This ancient light has been traveling toward us for nearly 14 billion years. It carries information about conditions in the early universe, encoded in those tiny temperature variations that span the entire sky. The night air moves gently past your window. What makes these patterns particularly interesting is how they connect to the idea of cosmic inflation. If the universe underwent a period of rapid expansion in its earliest moments, that process would have stretched quantum fluctuations to cosmic scales. Those stretched fluctuations would have left their mark on the cosmic microwave background. Take your time. The patterns we observe today might be the fossilized remains of quantum events that occurred when the universe was smaller than an atom. Darkness holds these ancient photons as they complete their long journey through space. Different theories about the early universe predict different patterns in this background radiation. By comparing observations with predictions, researchers can test ideas about cosmic inflation and the possibility of bubble universes. The evidence doesn't provide definitive proof, but it offers subtle clues about processes that occurred long before stars and galaxies existed. Some of these clues suggest that our observable universe might indeed be just one region within a much larger structure. The stillness around you mirrors the stillness between distant galaxies. Inflation theory describes the early universe as undergoing exponential expansion, with space itself stretching faster than the speed of light. This process could have created regions that became causally disconnected from each other, evolving into separate pocket universes with potentially different physical properties. Each pocket would have its own cosmic horizon, its own collection of galaxies and stars, its own version of the cosmic microwave background radiation. For a moment, your breathing finds its own gentle rhythm in the quiet night. From this perspective, cosmic inflation isn't just something that happened once in the distant past, but an eternal process that generates an infinite variety of cosmic environments. Our universe would represent just one outcome among countless others, each with its own unique combination of physical constants and initial conditions. The cool air carries these possibilities, like wind carries seeds. What's remarkable about this picture is how it connects the very largest scales of existence with the very smallest. Quantum fluctuations that occur at subatomic scales get amplified by inflation to become the variations we observe across the entire cosmic microwave background. The boundary between the quantum world and the classical world becomes less distinct when viewed from this cosmic perspective. Slowly, the same processes that create uncertainty at the particle level might be responsible for the diversity of cosmic environments at the largest scales. Silence fills the space between your thoughts. This connection between quantum mechanics and cosmology opens up new ways of thinking about the many worlds interpretation. Instead of parallel realities branching off from quantum measurements, we might have parallel realities existing as separate regions of space, each evolving according to its own version of physical law. The multiverse becomes not just a collection of abstract possibilities, but a concrete physical structure with different regions exploring different ways of organizing matter and energy. The darkness beyond your window holds all these distant possibilities. Observational cosmology continues to refine our understanding of these connections. New telescopes and more sensitive instruments allow researchers to map the cosmic microwave background with ever greater precision. Each improvement in measurement reveals new details about the patterns encoded in that ancient light. These observations don't just tell us about our own cosmic history, but potentially about the larger structure of which our universe might be a part. Just for a moment, your thoughts settle like dust settling in still air. The search for evidence of other universes requires incredible patience and precision. The signals, if they exist, would be extraordinarily subtle. They might appear as slight anomalies in the cosmic microwave background, or as unexpected patterns in the distribution of galaxies, or as tiny correlations that emerge only after analyzing vast amounts of data. The evidence would never be as direct as looking through a telescope and seeing another universe. Instead, it would come in the form of statistical patterns and theoretical consistency checks. The night holds these subtle mysteries in its vast embrace. What makes this search particularly challenging is that we can only observe from our single vantage point within our own cosmic horizon. We can't step outside our universe to get an external perspective on the larger structure of reality. All our information must be gathered from within, like trying to understand the architecture of a building while being confined to a single room, in the quiet. Yet even from this limited perspective, we can make inferences about what might exist beyond our direct observation. The quiet room around you contains its own hidden complexities. Quantum field theory provides another lens through which to examine these questions. The vacuum of space isn't truly empty, but filled with quantum fields that fluctuate even in the absence of particles. These fluctuations create a kind of background activity that permeates all of space. During cosmic inflation, these quantum fluctuations would have been stretched and amplified, potentially creating the variations we observe in the cosmic microwave background. The stillness between heartbeats mirrors the apparent stillness of empty space. The same quantum fields that create these cosmological patterns also govern the behavior of particles in laboratory experiments. The connection between the cosmic and the quantum becomes a bridge for testing ideas about the multiverse. Advances in our understanding of quantum field theory inform cosmological models, while cosmological observations provide new contexts for understanding quantum mechanics. And gently, this interplay between different scales of physics creates a web of connections that spans from the smallest to the largest structures in nature. Darkness flows around these connections, like water flows around stones. The cosmic microwave background also reveals information about the geometry of space itself. The patterns of hot and cold spots tell us whether space is curved or flat, whether it will expand forever or eventually collapse back on itself. These geometric properties provide constraints on theories about cosmic inflation and the possible existence of other universes. A flat universe, which observations suggest we inhabit, is consistent with many models of eternal inflation. Your breathing creates its own gentle rhythm in the surrounding quiet. The precision required to extract this information from the cosmic microwave background represents one of the great achievements of modern observational science. The temperature variations that carry this cosmic information are incredibly small, measured in millionths of a degree. Very softly, detecting and mapping these variations requires instruments that can measure temperature differences smaller than those created by the heat from a single candle, viewed from thousands of miles away. Yet these tiny signals carry information about the fundamental structure of reality. The cool air holds these measurements like memory holds experiences. What emerges from all these observations is a picture of a universe that's far more dynamic and creative than previous generations imagined. Instead of a static cosmos with fixed properties, we see a reality that's constantly exploring new possibilities, generating new structures, potentially creating new regions of space with their own unique characteristics. The multiverse, whether it exists as parallel quantum realities or as distant cosmic regions, represents this creative aspect of existence taken to its logical extreme. The night sky above you participates in this ongoing creativity. Even the process of making these observations changes our relationship to the cosmos. When we measure the cosmic microwave background, we're detecting photons that have been traveling through space since the universe was less than 400,000 years old. Take your time. These particles of light carry information across billions of years and trillions of miles to reach our instruments. In a sense, we're touching the early universe every time we make these measurements. Silence surrounds this ancient connection between past and present. The technology required for these observations has led to unexpected discoveries in other areas of science. The sensitive detectors developed for cosmology have found applications in medical imaging and material science. The data analysis techniques used to extract patterns from the cosmic microwave background have influenced fields ranging from artificial intelligence to climate modeling. The search for other universes generates knowledge that enriches our understanding of this universe. Your thoughts move through the quiet space, like light moves through cosmic distances. What's particularly striking about the cosmic microwave background is how uniform it appears across the entire sky. For a moment, the temperature variations that carry so much information are tiny deviations from an otherwise remarkably smooth distribution. This uniformity suggests that widely separated regions of the early universe were once in thermal contact, able to exchange energy and reach the same temperature. But according to standard cosmology, these regions should never have been in contact. The universe expanded too quickly for light to travel between them. The darkness around you holds this cosmic puzzle. Cosmic inflation provides an elegant solution to this puzzle. If the universe underwent rapid expansion in its earliest moments, regions that are now widely separated could have been in close contact before inflation began. The expansion would have stretched these regions apart, while preserving their thermal equilibrium. This explanation for the uniformity of the cosmic microwave background represents one of the strongest pieces of evidence supporting inflation theory. The stillness between your thoughts mirrors the equilibrium of that ancient radiation. But inflation theory also predicts that this process should have created quantum fluctuations that were stretched to cosmic scales. These fluctuations would have created tiny variations in density that eventually grew into the galaxies and galaxy clusters we observe today. Slowly, the same process that explains the uniformity of the cosmic microwave background also explains its subtle variations. The theory connects the smoothest and the most structured aspects of the universe within a single framework. This connection between uniformity and structure reveals something profound about the nature of cosmic evolution. The quiet room around you mirrors this balance between order and complexity. The patterns we observe in the cosmic microwave background also provide clues about the total amount of matter and energy in the universe. Different types of matter and energy leave distinct signatures in these ancient photons. Ordinary matter, the stuff that makes up stars and planets and people, accounts for less than 5% of the universe's total content. The rest consists of dark matter and dark energy, mysterious components that we can detect through their gravitational effects but cannot observe directly. Just for a moment, your breathing continues its steady rhythm, while these cosmic mysteries unfold. Dark matter reveals itself through the way galaxies rotate and the way light bends around massive galaxy clusters. Without this invisible matter, galaxies would fly apart, and the large-scale structure of the universe would look completely different. Dark energy, even more mysterious, appears to be accelerating the expansion of the universe itself. These discoveries emerged from careful observations of distant supernovae and measurements of the cosmic microwave background. The darkness outside your window participates in these cosmic mysteries. What makes these findings particularly intriguing is how they connect to theories about the multiverse. Different regions of an inflating cosmos might have different amounts of dark matter and dark energy. Some regions might have so much dark energy that they expand too rapidly for stars and galaxies to form. Others might have so little that they collapse back on themselves before complex structures can develop. Our universe appears to exist in a narrow range where the balance allows for the formation of stars, planets, and ultimately life. In the quiet, the stillness around you holds this delicate balance. This observation has led some physicists to consider whether the apparent fine-tuning of our universe's properties might be explained by the existence of many universes with different characteristics. In an infinite multiverse, every possible combination of physical constants and initial conditions would be realized somewhere. We find ourselves in a universe compatible with our existence, simply because we couldn't exist anywhere else. The cool air carries this thought like it carries sound. But this reasoning raises new questions about the nature of probability and observation. How do we calculate the likelihood of finding ourselves in a universe with particular properties when we can only observe the one universe we inhabit? Different approaches to this problem lead to different predictions about what we should expect to observe. Your heartbeat provides a steady reference point in the surrounding quiet. And gently, these questions connect to deeper issues in the philosophy of science. What does it mean to test a theory that makes predictions about unobservable regions of reality? How do we distinguish between a successful scientific explanation and an untestable speculation? The multiverse pushes these questions to their limits. Some scientists argue that the multiverse represents a natural extension of well-established physics, while others contend that it ventures beyond the boundaries of empirical science. The night air holds these debates like it holds the sound of distant traffic. Yet even these philosophical challenges have led to practical advances in our understanding. The attempt to develop testable predictions from multiverse theories has driven innovations in cosmology and quantum mechanics. New mathematical techniques have emerged from the effort to make sense of infinite collections of universes. The search for indirect evidence has sharpened our ability to extract information from subtle observational signals. Silence flows around these developments, like water flows around stones. One approach to testing multiverse theories involves looking for signatures of collisions between different bubble universes, very softly. If our cosmic region occasionally encountered another expanding bubble, the collision might leave detectable patterns in the cosmic microwave background. These patterns would appear as circular features, with specific temperature and polarization characteristics. Several research groups have searched for such signatures, though none have been definitively detected. The quiet room around you contains its own hidden patterns. Another potential test involves examining the statistical properties of the cosmic microwave background in unprecedented detail. Different models of cosmic inflation make different predictions about the precise nature of the quantum fluctuations that seeded cosmic structure. By measuring these fluctuations with extraordinary precision, we might be able to distinguish between models that predict a multiverse and those that don't. Future space-based observatories may have the sensitivity required for such measurements. Your breathing creates gentle variations in the surrounding stillness. The search for gravitational waves has opened another window into the early universe. Take your time. These ripples in space-time itself carry information about cosmic events that occurred when the universe was far too young and hot for light to travel freely. Primordial gravitational waves, if they exist, would provide direct evidence of cosmic inflation. The patterns of these waves might also carry signatures of the larger multiverse structure. The darkness above you participates in this cosmic symphony. Current gravitational wave detectors have revealed collisions between black holes and neutron stars, confirming Einstein's predictions about the nature of spacetime. But detecting primordial gravitational waves requires even more sensitive instruments. These signals would be extraordinarily faint, buried beneath noise from countless other sources. The technical challenges involved in such measurements push the boundaries of experimental physics. The cool air around you holds these technical marvels, like memory holds experiences. What emerges from all these investigations is a picture of science at the edge of its traditional boundaries. The multiverse represents a frontier where observation, theory, and philosophy intersect in complex ways. Whether or not other universes actually exist, the attempt to understand them has deepened our knowledge of this universe. For a moment, the questions themselves have proven as valuable as any potential answers. Your thoughts move through the quiet space, like light moves through cosmic distances. The cosmic microwave background continues to reveal new secrets as our instruments become more sophisticated. Recent observations have detected subtle polarization patterns that provide additional information about the early universe. These patterns arise from the way photons scattered off electrons in the hot plasma that filled space before atoms formed. The polarization carries independent information that can confirm or challenge our theoretical models. The stillness between heartbeats mirrors the ancient interactions that created these signals. These polarization measurements have already ruled out some models of cosmic inflation while supporting others. They've also provided new constraints on the total number of different types of particles that existed in the early universe. Each new measurement adds another piece to the cosmic puzzle. Slowly, the precision of these observations continues to improve with each new generation of instruments. Silence surrounds this ongoing dialogue between theory and observation. The study of cosmic structure on the largest scales provides another avenue for testing our understanding. Surveys that map the positions of millions of galaxies reveal patterns that echo the quantum fluctuations present during cosmic inflation. The way matter clusters on different scales carries information about the fundamental physics that govern the universe's earliest moments. These large-scale patterns complement the information encoded in the cosmic microwave background. The night sky above you participates in this vast cosmic web. What particularly remarkable is how observations made across vastly different scales and epochs all point toward a consistent picture of cosmic evolution. The same physical processes that explain the cosmic microwave background also predict the observed distribution of galaxies and the abundance of light elements like hydrogen and helium. This convergence of evidence from multiple independent sources strengthens our confidence in the underlying theoretical framework. Your breathing continues its steady rhythm while these cosmic connections unfold, just for a moment. Yet this convergence also reveals the profound scales involved in cosmic evolution. The light we observe from the cosmic microwave background has been traveling toward us for nearly 14 billion years. The room holds this ancient journey in its quiet corners. When that light began its voyage, The universe was a hot, dense plasma where atoms couldn't yet form. Electrons and protons moved freely through space, scattering photons in all directions. Only when the universe cooled enough for these particles to combine into neutral hydrogen did space become transparent to light. This moment of transparency happened everywhere at once, creating a sphere of last scattering that surrounds us at every distance we look. Your pulse marks time, while this cosmic sphere expands away from us at the speed of light. The photons we detect today carry the imprint of conditions at that moment of transparency. Their slight temperature variations map the density fluctuations that would eventually grow into galaxies and galaxy clusters. In the quiet, these same fluctuations, amplified by billions of years of gravitational growth, now form the cosmic web of matter we observe today. The connection spans almost the entire history of the universe. Cool air moves through the space around you like time moves through cosmic history. What makes these observations particularly powerful is their independence from local conditions. The cosmic microwave background provides a snapshot of the universe when it was only 380,000 years old. Galaxy surveys show us cosmic structure as it appears today. The agreement between these vastly different epochs confirms our understanding of how gravity shapes matter over cosmic time. This consistency extends to the smallest details we can measure. The quiet darkness participates in these ancient patterns. Observations of distant supernovae add another layer to this cosmic story. These stellar explosions serve as standard candles, allowing astronomers to measure distances across billions of light-years. The brightness of these explosions reveals how fast different parts of the universe were receding from us at different times in cosmic history. And gently, these measurements led to the discovery that cosmic expansion is accelerating. Your breathing creates gentle rhythms in the surrounding stillness. This acceleration suggests that space itself contains a form of energy that pushes against gravitational attraction. The nature of this dark energy remains one of the deepest mysteries in modern physics. It appears to make up about 70% of everything in the universe, yet we can only detect it through its gravitational effects. The presence of dark energy affects how we think about the multiverse. Silence flows around these cosmic mysteries, like water flows around hidden stones. If dark energy maintains its current properties, our observable universe will continue expanding and cooling indefinitely. Distant galaxies will eventually recede beyond our cosmic horizon, disappearing from view. The cosmic microwave background will stretch to longer and longer wavelengths until it becomes undetectable. Our descendants billions of years from now will inhabit a much lonelier cosmos. Very softly, the cool night air carries this distant future, like memory carries the past. But even in such a far future, the fundamental questions about the multiverse would remain. If other bubble universes exist beyond our horizon, they would continue their own independent evolution. Some might experience different phases of expansion or contraction. Others might develop entirely different physical laws or fundamental constants. The vast majority would remain forever beyond our ability to observe or influence. Your heartbeat provides a steady reference point while these cosmic scales unfold. This limitation of observation doesn't diminish the scientific value of multiverse theories. Many of our most successful scientific ideas began as untestable speculations that later found empirical support. The existence of atoms was debated for centuries before direct evidence became available. The reality of other galaxies beyond our own was controversial until the 1920s. Science often advances by taking theoretical leaps that observations later confirm or refute. The darkness above you holds these leaps of understanding like space holds distant light. What distinguishes scientific speculation from mere fantasy is its connection to established physics and its potential for generating testable predictions. Take your time. Multiverse theories emerge naturally from our best current understanding of cosmic inflation and quantum mechanics. They make specific predictions about what we should observe in our own universe. These predictions provide the bridge between theory and observation. Stillness surrounds these connections, like silence surrounds sound. The search for these predictions has led to increasingly sophisticated observational programs. Space-based telescopes now measure the cosmic microwave background with extraordinary precision. Ground-based surveys map the distribution of galaxies across billions of light-years. Gravitational wave detectors listen for ripples in space-time itself. Each new observation either supports or challenges our theoretical understanding. The quiet room around you participates in this ongoing cosmic conversation. What emerges from these efforts is a picture of a universe far stranger and more wonderful than previous generations could have imagined. For a moment, the familiar world of planets and stars represents only a tiny fraction of cosmic reality. Most of the universe consists of dark matter and dark energy that we can barely detect. The observable universe itself might be just one small region in an infinite multiverse. Your thoughts drift through this vastness, like clouds drift through an endless sky. Yet even as these discoveries humble our cosmic perspective, they also reveal the remarkable power of human understanding. From our small planet, we can probe the deepest structures of reality. We can trace cosmic history back to moments after the universe began. We can detect the faint echoes of quantum fluctuations that occurred when space itself was smaller than an atom. This ability to comprehend such scales represents one of the greatest achievements of human civilization. The cool air around you carries these achievements like wind carries distant music. Each equation represents countless hours of thought and experimentation. The instruments that test these theories push the boundaries of human engineering and ingenuity. Slowly, the collaboration required spans continents and generations. Silence flows between these human connections, like space flows between distant galaxies. What makes this scientific enterprise particularly remarkable is its cumulative nature. Each generation builds upon the discoveries of previous ones. The cosmic microwave background was predicted decades before it was observed. Gravitational waves were anticipated a century before their detection. The multiverse theories of today might find observational support in ways we cannot yet imagine. The darkness holds these future possibilities, like night holds the promise of dawn. Even if direct evidence for other universes remains elusive, the theoretical framework that predicts them continues to deepen our understanding of this universe. The same physics that suggests bubble universes also explains the observed properties of space and time. The quantum mechanics that leads to many worlds interpretations also enables the technologies that surround us. These connections between abstract theory and concrete reality demonstrate the unity of scientific knowledge. Your breathing creates gentle variations in the surrounding quiet. Just for a moment. The questions raised by multiverse theories also illuminate the nature of scientific inquiry itself. What constitutes adequate evidence for extraordinary claims? How do we balance theoretical exigence with empirical verification? When does speculation become science, and when does it venture into philosophy? These questions have no simple answers, but asking them sharpens our understanding of how knowledge grows. The stillness between heartbeats mirrors the pauses between cosmic discoveries. What remains constant through all these investigations is the human drive to understand our place in the cosmos. Whether we inhabit one universe or countless universes, whether reality branches with every quantum measurement or follows a single trajectory, we find ourselves here, now, capable of contemplating these profound questions. This capacity for wonder and understanding might be the most remarkable feature of our cosmic story. The quiet night air holds this story, like space holds the light of distant stars. The wonder we feel when contemplating these questions connects us to something larger than ourselves. Your thoughts settle into the rhythm of this cosmic inquiry. In the quiet, perhaps the most profound aspect of multiverse theories isn't what they tell us about other realities, but what they reveal about the nature of existence itself. If infinite universes branch from every quantum event, then every possible story unfolds somewhere in the vast expanse of reality. Every choice leads to a different world. Every moment splits into countless alternatives. The cool air around you holds these branching possibilities, like a tree holds its many leaves. In some of these alternate realities, the fundamental constants of physics take different values. Gravity might be stronger or weaker. The electromagnetic force might behave differently. These variations would create universes with entirely different evolutionary paths. Some might never form stable atoms. Others might be filled with exotic forms of matter we can barely imagine. The darkness outside your window encompasses these alien possibilities. Yet for all their strangeness, these alternate universes would still follow mathematical laws. And gently, the same principles that govern quantum mechanics and relativity would apply everywhere. The patterns we discover through human thought seem to reflect deep structures that transcend any single universe. Stillness flows around these mathematical truths, like water flows around ancient stones. This universality of mathematical law provides one way to think about what makes different universes part of the same multiverse. They share common underlying principles, even as they express those principles in radically different ways. A universe where electrons have different masses would still obey the same quantum mechanical rules that govern electron behavior in our reality. The quiet room participates in these shared mathematical foundations. Some physicists find this mathematical unity deeply compelling evidence for the multiverse. If the laws of physics are truly universal, they argue, then those laws should generate all possible configurations of matter and energy. The multiverse contains every solution. Your heartbeat provides a gentle counterpoint to these infinite solutions. Others remain skeptical of such reasoning. They point out that mathematical possibility doesn't necessarily imply physical reality. Very softly, the gap between mathematical description and physical existence remains one of the deepest puzzles in the philosophy of science. The air grows cooler as these philosophical questions deepen. This tension between mathematical elegance and empirical verification runs through many areas of modern physics. String theory predicts extra dimensions of space that we cannot directly observe. Quantum field theory describes virtual particles that exist only in calculations. The boundary between useful mathematical tools and claims about reality becomes increasingly subtle. Silence surrounds these subtle boundaries, like night surrounds distant lights. Yet even if multiverse theories never achieve direct empirical confirmation, they serve important functions in scientific thinking. They help us understand why our universe has the particular properties we observe. They suggest new ways to interpret quantum mechanics and cosmology. They expand our conception of what reality might encompass. The darkness holds these expanded conceptions, like space holds distant galaxies. The process of developing and testing these theories also drives technological innovation. Take your time. The instruments needed to measure cosmic background radiation push the limits of detector sensitivity. The computers required to simulate cosmic evolution demand ever greater processing power. The mathematical techniques developed to analyze multiverse models find applications in fields far removed from cosmology. Your breathing creates gentle variations in the surrounding stillness. These practical benefits emerge even when the original theoretical questions remain unresolved. The search for gravitational waves led to advances in laser interferometry that now benefit many areas of science and technology. The study of quantum entanglement inspired new approaches to computation and communication. The exploration of cosmic inflation deepened our understanding of phase transitions in condensed matter physics. The quiet night air carries these unexpected connections, like wind carries distant sounds. This pattern of theoretical exploration leading to practical discovery reflects a deep feature of scientific progress. Questions that seem purely abstract often generate insights with concrete applications. The distinction between basic and applied research becomes less meaningful when viewed across longer timescales. Today's speculative theory might become tomorrow's transformative technology. For a moment, stillness flows between these transformations like water flows between stepping stones. The multiverse theories of our era will likely undergo similar evolution. Some aspects will find empirical support and become accepted parts of scientific knowledge. Others will be refined or abandoned as new observations become available. The questions they raise will inspire new generations of scientists to push the boundaries of human understanding even further. The cool air around you participates in this ongoing evolution of ideas. What remains constant through these changes is the human capacity to imagine realities beyond immediate experience. The same cognitive abilities that allow us to contemplate alternate universes also enable art, literature, and music. The boundary between scientific speculation and creative imagination becomes surprisingly fluid when we consider the deepest questions about existence. Your thoughts drift through this fluid boundary like clouds drift through an endless sky. Perhaps this is why multiverse theories capture public imagination so powerfully. Slowly, they speak to something fundamental in human nature, our desire to explore beyond the known, to imagine what lies beyond the horizon. Whether those horizons are geographical, technological, or cosmic, The impulse to cross them drives much of human achievement. The darkness above you holds these achievements, like night holds the memory of day. The scientists who develop multiverse theories are explorers in the truest sense. They venture into realms of possibility that no human has ever contemplated before. They chart territories of thought that expand the boundaries of human knowledge. Silence surrounds these territories like space surrounds distant stars. Their work requires a different kind of courage than physical exploration demands. The room holds this quiet courage like it holds the gentle sound of your breathing. When astronomers point their telescopes toward the edge of space, they're looking backward through time itself. Light from distant galaxies carries information about how the universe appeared billions of years ago. The farther they look, the younger the cosmos becomes in their instruments. Just for a moment, each photon has traveled for eons to reach us. This creates a natural boundary to what we can observe. Not because there's a wall at the edge of space, but because light from beyond a certain distance simply hasn't had enough time to reach us yet. The universe is old, but not infinitely old. Your heartbeat marks time in this moment, while cosmic time stretches across vast scales. Think of it like standing in a field at night with a flashlight. You can see clearly for a certain distance. Then the light fades into darkness. But that darkness doesn't mean nothing exists beyond your beam. It just means you can't see it yet. The cosmic version works the same way, except instead of a flashlight beam, we're limited by the age of the universe itself. Cool air moves gently around these invisible boundaries. Beyond this observational horizon, space continues. In the quiet, galaxies form and evolve. Stars are born and die. The same physical processes that shape our visible universe unfold in regions we may never see directly. Some of those distant regions might be very different from our local neighborhood. The darkness outside your window connects to these unseen territories through the fabric of space itself. During the earliest moments after the universe began, different regions expanded so rapidly that they lost contact with each other. Like bubbles forming in boiling water, separate domains of space inflated at tremendous speeds. Each bubble became its own cosmic realm. These domains might have slightly different properties. The forces that govern matter and energy could take different strengths. The particles that make up atoms might have different masses. Each bubble universe would evolve according to its own particular rules. Stillness surrounds these countless bubbles, like silence surrounds distant conversations. We live inside one such bubble, observing only our local cosmic neighborhood. The other bubbles remain beyond our horizon, following their own evolutionary paths. Some might be empty of matter, others might be filled with forms of matter we've never encountered. And gently, this picture emerged from studying how space itself can expand. When physicists traced the expansion backward to its beginning, they discovered that the early universe must have gone through a period of incredibly rapid growth. During those first tiny fractions of a second, space stretched faster than light could travel across it. The quiet room around you once participated in that ancient expansion, when all of space was smaller than an atom. That rapid expansion explains many features of our observable universe. It explains why space appears flat rather than curved. It explains why the temperature of the cosmic background radiation looks nearly the same in all directions. But it also suggests that our observable region is just one small part of a much larger whole. Your thoughts drift through this larger whole, like leaves drift on a vast ocean, very softly. The same process that created our bubble likely created countless others. Each began with its own random quantum fluctuations. Each developed its own unique combination of physical properties. Each became a complete universe in its own right. Most of these bubble universes would be uninhabitable by any form of life we can imagine. The air grows cooler as you contemplate these lifeless realms. In some bubbles, gravity might be too strong, causing all matter to collapse into black holes before stars could form. In others, gravity might be too weak, preventing gas clouds from condensing into stars at all. The electromagnetic force might be so different that atoms couldn't hold together. Only a tiny fraction of bubble universes would have conditions suitable for complexity to emerge. The darkness holds these rare, life-friendly bubbles, like night holds scattered lights across a vast landscape. We find ourselves in one of these exceptional bubbles, not because we're special, but because we couldn't exist anywhere else. Life can only observe universes where life is possible. Take your time. This creates a kind of selection effect in what we see. It's like asking why all the fish you catch live in water. Silence flows around this simple logic, like water flows around smooth stones. This reasoning helps explain why our universe seems so perfectly tuned for the existence of stars, planets, and living things. Not because it was designed that way, but because we can only observe universes where such tuning occurred by chance. In the vast majority of bubble universes, there's no one around to notice how the forces work. Your breathing creates gentle variations in the stillness that surrounds these unobserved realms. But bubble universes represent just one way the multiverse might be structured. Another possibility emerges from the strange behavior of quantum systems when they're measured or observed. Every quantum measurement seems to produce a definite result from a range of possibilities. The cool air around you participates in countless quantum events each moment. For a moment, before measurement, quantum systems exist in what physicists call superposition, a combination of all possible states simultaneously. An electron can be spinning in multiple directions at once. A particle can be in several locations simultaneously. But when we observe the system, we always see just one definite outcome. The room holds this mystery, like it holds the gentle sound of your heartbeat. One way to understand this transition from many possibilities to one reality is to imagine that all possibilities actually occur. Each potential outcome happens in its own separate branch of reality. When you observe the electron, you don't collapse the superposition, you just find yourself in one particular branch. Stillness surrounds these branching realities, like space surrounds distant stars. In this picture, every quantum event splits the universe into multiple copies. In one copy, the electron spins up. In another copy, it spins down. Both versions of you exist, each observing their own definite result. The splitting happens constantly. At every quantum interaction, your thoughts drift through this constantly branching tree of possibilities. Slowly. This means that somewhere in the multiverse, every possible version of history has unfolded. In some branches, dinosaurs never went extinct. In others, humans evolved differently or not at all. Every choice you've ever made led to a different outcome in some parallel reality. The darkness outside encompasses all these alternative histories. Each branch remains completely separate from all the others. You can never communicate with your alternate selves or travel between branches. Each version of reality is complete and self-contained. The air grows cooler as you contemplate these isolated parallel worlds. This branching picture makes very different predictions than the bubble universe model. Instead of distant regions of space with different physical laws, it suggests nearby realities with different histories but identical physics. Both ideas expand our conception of what exists beyond direct observation. The quiet night holds both possibilities, like it holds the memory of ancient starlight. Just for a moment, these two approaches to the multiverse differ in what they suggest about the nature of reality itself. The air holds both possibilities without choosing between them. In the bubble model, each universe exists as a separate region of space, potentially with its own physical laws. The bubbles float in a larger cosmic sea, each one a complete domain with its own matter and energy. Distance separates these realms, vast, unreachable distance that no signal could ever cross. Your breath creates small movements in the stillness around these distant bubbles. The branching model suggests something entirely different. Here, all the parallel worlds occupy the same space, separated not by distance but by the branching paths of quantum events. Every version of reality unfolds in the same cosmic location, but along different threads of possibility. The room around you participates in both pictures simultaneously. Scientists have developed ways to look for hints that either model might be correct. The search requires incredible precision and patience, like listening for whispers in a quiet room. In the quiet, most of the evidence remains indirect, emerging from careful measurements of the cosmos we can observe. Darkness flows around these subtle investigations. One approach involves studying the cosmic microwave background, the faint afterglow of the universe's hot beginning. This ancient light carries information about conditions in the very early cosmos. If bubble universes exist, they might have left traces in this background radiation. The cool air around you once glowed with this same ancient light. When bubble universes form during cosmic inflation, they can sometimes collide with neighboring bubbles. These collisions would create ripples in space itself, patterns that might still be visible in the microwave background today. The patterns would appear as subtle variations in temperature across the sky. Stillness surrounds these faint cosmic echoes. Several research teams have searched for such collision signatures. They analyze maps of the microwave background, looking for circular patterns or other geometric shapes that don't match the random fluctuations expected from a single bubble universe. And gently, your thoughts drift through these careful measurements, like light drifts through space. So far, no clear collision signatures have been found. The microwave background appears consistent with our universe developing in isolation, without interference from neighboring bubbles. But the absence of obvious signals doesn't rule out the bubble model entirely. The quiet night holds both the presence and absence of these cosmic fingerprints. The collision signatures might be too subtle to detect with current instruments, or perhaps our bubble simply hasn't collided with any neighbors during the observable history of our universe. The search continues with increasingly sensitive measurements. Silence flows around these ongoing investigations. Testing the branching model presents different challenges, since each branch of reality remains completely isolated from all others. No direct communication between branches is possible. You can never receive a message from an alternate version of yourself. The darkness encompasses all these unreachable parallel selves. Instead, researchers look for indirect signs that quantum branching might be occurring. They study the fundamental behavior of quantum systems, searching for clues about what happens during measurement events. Very softly, the air grows cooler as these quantum mysteries deepen. Some experiments attempt to create quantum superpositions involving larger and larger objects. If the branching model is correct, then every object, no matter how big, should be able to exist in superposition until it's observed. The challenge lies in isolating large objects from their environment, long enough to maintain the superposition. Your breathing creates gentle disturbances in the quantum fields around you. Other tests focus on the precise timing and statistics of quantum measurements. Different interpretations of quantum mechanics make slightly different predictions about how measurement outcomes should be distributed. By performing thousands of identical quantum experiments, researchers can look for patterns that might reveal which interpretation matches reality. Stillness surrounds these statistical investigations. The results remain ambiguous. Quantum mechanics works perfectly for making predictions, but the deeper question of what happens to unmeasured possibilities continues to puzzle physicists. Take your time. The branching model remains one possibility among several. The quiet room holds this uncertainty like it holds the gentle sound of distant traffic. Both multiverse models face the same fundamental challenge. They make claims about regions of reality that lie forever beyond direct observation. This puts them at the edge of what science can traditionally investigate. Darkness flows around this boundary between the known and unknowable. Science typically advances by making predictions that can be tested through observation or experiment. Theories that make no testable predictions risk becoming philosophy rather than physics. The multiverse models walk carefully along this line. The cool air around you carries both scientific questions and philosophical implications. Yet even untestable theories can have scientific value if they emerge naturally from well-tested principles. The bubble universe model arises from cosmic inflation, which successfully explains many observed features of our universe. The branching model emerges from quantum mechanics, which has passed every experimental test for nearly a century. For a moment, your thoughts drift through this intersection of established science and speculative possibility. Sometimes the most profound scientific insights come from taking successful theories seriously and following their implications wherever they lead. Even if those implications extend beyond the reach of direct observation, stillness surrounds these bold extrapolations from known physics. The multiverse models also raise questions about the nature of scientific explanation itself. Traditionally, science seeks to explain why our universe has the particular properties we observe. Why do the forces have the strengths they do? Why did the early universe have the specific conditions that led to the formation of stars and galaxies? The quiet night encompasses both the questions and their possible answers. In a single universe, these might seem like fundamental mysteries requiring special explanations. But in a multiverse containing all possible variations, our particular combination of properties becomes less mysterious. We observe this specific set of conditions because we exist in the subset of universes where such conditions occurred by chance. Slowly, the air holds this shift in perspective, like it holds the memory of ancient conversations. This reasoning changes the types of questions science might ask. Instead of wondering why our universe has life-friendly properties, we might ask what fraction of all possible universes would be expected to have such properties. Instead of seeking special explanations for cosmic fine-tuning, we might study the statistical distribution of physical constants across the multiverse. Darkness flows around these new ways of thinking about cosmic questions. Some physicists find this approach deeply satisfying. It transforms apparent cosmic coincidences into natural consequences of living in a vast ensemble of possibilities. Others worry that it makes science less predictive and more dependent on assumptions about unobservable realms. The room around you holds both perspectives without judgment. The debate continues in research papers and conference presentations as scientists work to understand what kinds of evidence might eventually resolve these questions. New theoretical developments occasionally suggest novel ways to test multiverse ideas. Your breathing creates small variations in the stillness that surrounds these ongoing discussions. Just for a moment, advanced theories of quantum gravity sometimes predict specific relationships between different branches of the multiverse. These relationships might leave detectable signatures in the cosmic microwave background, or in the behavior of fundamental particles. Silence encompasses these theoretical possibilities. Future space missions will map the microwave background with unprecedented precision. New particle accelerators will probe quantum mechanics at higher energies than ever before. Each advance in observational capability opens new windows for testing ideas about the larger structure of reality. The cool air around you participates in this gradual expansion of human knowledge. Even if direct evidence for the multiverse remains elusive, the ideas themselves have already influenced how physicists think about fundamental questions. They've inspired new mathematical techniques for studying cosmic evolution and quantum measurement. Stillness flows around these intellectual developments. The multiverse concepts have also sparked conversations between physics and philosophy about the nature of existence, consciousness, and scientific knowledge. In the quiet, these discussions help clarify what different theories actually claim and what kinds of evidence would be needed to support them. The quiet night holds these interdisciplinary conversations like it holds the light from distant stars. Whether or not the multiverse exists as a physical reality, it serves as a powerful tool for exploring the logical consequences of our best current theories. It pushes us to think more carefully about the relationship between what we can observe and what might actually exist. Darkness surrounds this expansion of conceptual boundaries. The search for evidence continues with new instruments and more sensitive measurements. Each observation adds another piece to our understanding of the cosmos, whether it supports multiverse models or points toward alternative explanations. The air grows cooler as these investigations extend deeper into the night of cosmic mystery. The instruments themselves tell stories through the patterns they detect. Your heartbeat keeps its own rhythm, while telescopes gather ancient light from the edge of what we can see. And gently, radio telescopes listen to the hum of hydrogen atoms scattered throughout space. These atoms emit a specific frequency when their electrons flip between energy states. By mapping this signal across the sky, astronomers can trace how matter moved and clumped together billions of years ago. The quiet room holds this invisible symphony of cosmic hydrogen. Some regions of space contain slightly more hydrogen than others. These variations might preserve echoes of processes that happened during the universe's earliest moments. If inflation created bubble universes, the boundaries between different regions could have left subtle imprints on how matter distributed itself. Stillness surrounds these faint cosmic fingerprints. The patterns appear as tiny temperature differences in the microwave background radiation. One patch of sky might be a few millionths of a degree warmer than another patch. These minute variations trace back to quantum fluctuations that got stretched to enormous scales during rapid expansion. The air around you participates in this ancient story written in temperature, very softly. Different models of inflation predict slightly different patterns in these temperature maps. Some versions suggest the expansion happened smoothly and uniformly. Others propose that inflation occurred in separate episodes, creating distinct regions with different properties. Darkness flows around these competing possibilities. The most sensitive measurements require satellites positioned far from Earth's atmosphere. These spacecraft spend years collecting photons that have traveled for nearly 14 billion years to reach their detectors. Each photon carries information about conditions when the universe was only a few 100,000 years old. Your breathing creates gentle waves in the quantum fields that connect you to this cosmic archaeology. The data arrives as millions of individual measurements, each recording the temperature of microwave radiation from a specific direction in space. Supercomputers analyze these measurements to extract patterns that might reveal the underlying physics of cosmic inflation. Silence encompasses the patient work of separating signal from noise. Some patterns would suggest that our observable region connects smoothly to similar regions beyond our horizon. Other patterns might indicate boundaries or transitions that could mark the edges of our particular bubble universe. Take your time. The cool night air holds both possibilities without favoring either. Gravitational wave detectors add another layer to this investigation. These instruments measure ripples in space-time itself, created when massive objects accelerate through the cosmos. The waves carry information about events that happened in regions of space where light cannot reach us. Stillness flows around these space-time vibrations. During inflation, quantum fluctuations in the gravitational field would have been stretched to cosmic scales, just like fluctuations in matter and energy. These gravitational waves might still be propagating through space, carrying signatures of the expansion process that created our local region of the multiverse. The quiet room resonates with frequencies too low for human ears to detect. Future gravitational wave observatories will be sensitive enough to detect these primordial signals. The wave patterns could reveal whether inflation happened once or multiple times, and whether it created a single expanding region or many separate bubble universes. For a moment, your thoughts drift through this intersection of present technology and future discovery. Particle accelerators contribute their own form of evidence by recreating conditions similar to those that existed during the universe's earliest moments. When particles collide at extremely high energies, they briefly reproduce the temperatures and densities that filled space during inflation. Darkness surrounds these controlled recreations of cosmic history. The particles created in these collisions behave according to the same quantum mechanical principles that governed the early universe. By studying how particles interact under extreme conditions, physicists can test whether their models of inflation match what actually happened during the first fraction of a second after expansion began. The air grows cooler as these experiments probe deeper into fundamental physics. Some collision experiments search for evidence of extra dimensions beyond the three spatial dimensions we experience directly. Theories that include additional dimensions often predict the existence of multiple universes or branes that could interact with each other through gravitational effects. Slowly, stillness holds these explorations of hidden spatial dimensions. If particles occasionally leak between different branes or dimensional regions, the missing energy might be detectable in carefully designed experiments. These searches look for events where the total energy before collision doesn't match the total energy of all detected particles afterward. The quiet night encompasses both the known and the mysteriously absent. Other experiments investigate whether the constants of nature might vary slightly in different regions of space or time. If bubble universes have different physical laws, the boundaries between regions might create gradual transitions in fundamental constants. Your breathing participates in this search for cosmic variation. Atomic clocks provide some of the most precise measurements possible of how physical constants behave over time. By comparing the frequencies of different atomic transitions across many years, researchers can detect changes as small as a few parts in a trillion. Silence flows around these extraordinarily sensitive measurements. The constants appear stable within our observable region. But this doesn't rule out variations that occur over larger scales or longer time periods. Just for a moment, if we live in one bubble among many, the differences might only become apparent when comparing regions separated by distances much larger than our cosmic horizon. The cool air around you connects to this vast scale of cosmic investigation. Quantum experiments continue to probe the nature of measurement and the reality of unmeasured possibilities. New techniques allow researchers to study larger and more complex quantum systems while maintaining their delicate superposition states. Stillness surrounds these investigations of quantum boundaries. Some experiments create quantum entanglement between particles separated by increasing distances. If the branching interpretation is correct, these experiments might eventually reveal subtle correlations that distinguish it from other ways of understanding quantum mechanics. The quiet room holds these quantum connections that span both space and possibility. Computer simulations play an essential role in interpreting all these different types of evidence. Researchers create detailed models of how the universe would evolve under different assumptions about inflation, quantum mechanics, and the fundamental laws of physics. In the quiet, darkness flows around these digital recreations of cosmic history. The simulations can predict what patterns should appear in the microwave background, what gravitational wave signals should reach our detectors, and what particle collision results should occur if various multiverse models are correct. Your thoughts drift through these computational explorations of theoretical possibilities. By comparing simulation predictions with actual observations, scientists can determine which models best match the evidence. This process gradually narrows the range of viable theories about the larger structure of reality. The air grows cooler as data and theory converge through careful comparison. Each new observation either supports existing models or reveals discrepancies that require new theoretical developments. Science advances through this ongoing dialogue between prediction and measurement, theory and evidence. Stillness encompasses this patient accumulation of cosmic understanding. The multiverse ideas have also inspired new mathematical techniques for dealing with infinite collections of possibilities. And gently, traditional probability theory assumes finite sets of outcomes. But bubble universes and branching quantum states involve potentially infinite ensembles. The quiet night holds these mathematical innovations like it holds the memory of ancient calculations. Researchers develop new ways to assign meaningful probabilities to events that occur across infinite multiverse collections. These mathematical tools help make precise predictions, even when dealing with concepts that extend beyond direct observation. Silence flows around these abstract explorations of infinite possibility. The techniques find applications beyond multiverse theory, contributing to advances in quantum computing, statistical mechanics, and information theory. Ideas originally developed to understand cosmic inflation now help design quantum algorithms and analyze complex datasets. Your breathing creates small disturbances in the stillness that surrounds these cross-connections between different fields of research. Philosophy of science continues to grapple with questions about what constitutes valid scientific knowledge when direct testing becomes impossible. These discussions help clarify the logical structure of multiverse arguments and their relationship to established scientific principles. The cool air around you participates in these ongoing conversations about the nature of scientific evidence. Very softly, some philosophers argue that theories making claims about unobservable regions should be judged by different criteria than theories about directly testable phenomena. Others maintain that the same standards of evidence should apply regardless of observational accessibility. Darkness holds both perspectives without resolving the tension between them. The debate influences how scientists present multiverse research and how funding agencies evaluate proposals for related investigations. It shapes the questions that graduate students choose to pursue and the problems that established researchers consider worth their time. Stillness flows around these practical consequences of abstract philosophical discussions. Public understanding of multiverse concepts continues to evolve through popular science books, documentaries, and educational programs. These efforts help people appreciate both the scientific foundations and the speculative aspects of current multiverse research. The quiet room encompasses both expert knowledge and broader cultural curiosity about cosmic questions. Science fiction writers and artists draw inspiration from multiverse ideas, creating stories and images that explore their implications for human experience and meaning. Take your time. These creative works sometimes suggest new ways of thinking about scientific questions, or highlight assumptions that researchers hadn't previously examined. Your thoughts drift through this interplay between scientific investigation and imaginative exploration. The multiverse concepts raise profound questions about the uniqueness and significance of human existence. If every possible outcome occurs somewhere in the branching structure of reality, what makes our particular experience special or meaningful? The air grows cooler as these questions extend beyond physics into territory where science meets philosophy and personal reflection. Different people find different answers to these questions. Some see the multiverse as diminishing human importance by making us just one instance among infinite variations. Others find it liberating to imagine that every possibility gets its chance to unfold somewhere in the vast structure of existence. Stillness surrounds these personal responses to cosmic possibility. The scientific investigation continues regardless of these philosophical and emotional reactions. Researchers design new experiments, analyze fresh data, and develop more sophisticated theoretical models. Each advance brings us closer to understanding whether the multiverse exists as physical reality or remains an intriguing theoretical possibility. For a moment, the quiet night holds both the ongoing search and its uncertain destination. New space missions will launch in the coming decades, carrying instruments capable of detecting signals that current technology cannot reach. These missions will map the cosmos with unprecedented precision and sensitivity. Darkness flows around these future explorations of cosmic structure. Advanced quantum computers might eventually simulate multiverse dynamics with enough detail to make testable predictions about observable phenomena. Thanks for being here tonight. Good night.